In this video, we'll be looking at unit conversions. So unit conversions and converting between different units is an incredibly important technique. In this video, we're going to look at some of the basics, but the basic strategies and tools that you develop in this are going to be used throughout the semester in order for you to do actually more chemistry related problems in future chapters. So we're going to take the techniques that we're learning here just for basic unit conversions, and we'll be applying these at different other places as our technique to solve chemistry problems throughout the semester. Kind of our first type of units that we're most familiar with are called English or imperial units. These are the units we're most familiar with. We use these in our everyday life. We've used these since we were children, really. And at this point, these are pretty much only used in the United States right now. Everywhere else in the world has gone off of these units and is using metric. But some of the English units that we're familiar with are 12 inches equals a foot, 2 cups in a pint, 4 quarts in a gallon, 3 feet in a yard, 4 cups in a quart, 16 ounces in a pound, and we could list a whole bunch of other ones. We're familiar with these because we've used these our entire lives. Even though we're familiar with these are somewhat strange and random. We're kind of familiar with these, but these are kind of strange units. There's not much of a pattern that follows for that. So that means if you're not already familiar with it, very familiar with it, this would be extremely difficult to learn fresh and kind of use. We're used to it. We're used to dealing with these units. We're used to kind of the strange conversions between the different units in this English system. But there's some limitations to this. There's no set pattern. It's not easy to follow. So being these English units are so strange, anytime you are needing to convert from one English unit to another English unit, I will provide for you the unit conversion you need. So you don't have to memorize any of these, even though you probably know a lot of these already. What we want to really focus on are metric or SI units. And the reason why we want to focus on these is these are used by the rest of the world. It's one of the reasons why we're not as familiar with these units. And we care so much about these is these are what's used in science, medicine, healthcare. You cannot have a career in a scientific, medical, or healthcare related field without being metric proficient. I'm actually going to use the term metric fluent, kind of thinking of it as a language. We're not as familiar with this language. We don't use it on a regular basis, but we have to become fluent. You really can't get anywhere in any of these fields without knowing the basics of the metric system. And the reason why the rest of the world uses it and why it's used almost exclusively in science, medicine, and healthcare is the metric system follows a regular pattern and is consistent with our base 10 number system. You're not having a lot of strange conversions. Everything's based on a power of 10. So here in this table, we kind of listed some of the most commonly used SI units, and I'm going to pare this down even more, kind of between the red lines, kind of between tera and nano. Anywhere between here, these are our most common units. Yes, there's some smaller ones that occasionally you end up using. There's some bigger ones that you occasionally have to use. But the ones between tera and nano are the ones you really need to be familiar with. You need to memorize what the prefix is, what the symbol is, and what that numerical meaning is, such that you're able to write conversions for yourself. That's part of what it means to be metric fluent, that you're comfortable enough in the system to do some basic things proficiently and quickly. There's a couple still in here. Hecto and deca are not commonly used. Don't worry about those. The key ones you want to work on memorizing are tera, giga, mega, kilo, then deci, centi, milli, micro, nano. That's our first step in kind of becoming metric fluent, is learning what these mean. And what you really should be doing is you should kind of flashcard these. For example, if we were trying to learn kilo, on one side of the flashcard we'd put kilo and the K, and then on the reverse side of that flashcard, that 3x5 card, we put the numerical meaning of 1,000. And then you can just go through and quiz yourself until you're feeling really good and really comfortable with these metric units, because you're going to see these metric units a lot. And that's part of kind of having a career in the medical and scientific areas, is making sure you can deal with the metric system cleanly and easily. Because we live our normal everyday life using the English system, we're buying gas, we're filling up in gallons, we're buying quarts and gallons of things in the grocery store, we're measuring things in inches and feet. But at the same time, we know that when we're doing science, when we're doing medicine, we need to be working in metric. There are equivalencies between the two systems. And you can kind of look, I wrote up some of them here for you. There's different equivalencies between the different units for mass, length, volume, and you notice they're kind of not set great. They kind of have strange numbers associated with them. Well, the reason why they have strange numbers associated with them is because component of that is that English system that's not working on base 10, powers of 10 very easily. So you get all these strange numbers that would be almost impossible to try to memorize. So there's no need to memorize conversions between English and metric. I will always give you one conversion for each dimension. So what that means is, if we look at length, I listed a bunch of different metric and English conversions here. 1 meter, 1.094 yards, 1 yard, 0.914 meters, 1 meter, 39.37 inches, 1 inch, 2.54 centimeters, 1 kilometer, 0.6214 miles. I wouldn't give you all of these. I would give you one of these for each unit. So you'd get one of these for length, you'd get one of these for mass, you'd get one of these for volume. Then, being you already have other English to English conversions, as long as you know metric to metric conversions, you only ever need one of these equalities for each quantity or dimension. You don't need them all, because you can get to where you need to be by using other things and your knowledge of the metric system. So the technique we're going to use to solve quantitative problems this semester, almost all of them get done in this way. I'd say over 95% of the calculations we do generally are going to be the form of dimensional analysis. So what dimensional analysis is a technique used for converting between units. Not only are we going to do it with basic unit conversions here, we're going to see in future chapters how we can use this for future chemistry problems that are more chemistry specific. And the reason why dimensional analysis is a great technique is dimensional analysis organizes calculations in multi-step problems. It clearly lets you see where you started at, where you're currently at, and then what you still need to do. And it also shows you exactly kind of what mathematical operation has to happen. The focus on, when we're doing dimensional analysis, is on units. That's what we're focused on. We're not so focused on the numbers, we're focused on the units. If we change the units in the proper way, that's our strategy, focus on the units, the numbers associated with those units are going to go along for the ride, and we're going to do the right thing with the numbers. So we really want to focus on the units. What unit are we at? What unit are we trying to get to? So we've already written a lot of equalities up. I rewrote one here. 1 kilometer is 0.6214 miles. Now, anytime you have an equality, you can express that equality as a ratio. And here's how I kind of express that ratio. Ratio could be either way. We could have the kilometers on the top and the miles on the bottom, or we can have the miles on the top and the kilometers on the bottom. Each one of these three, this equality, this ratio, and this ratio, are all explaining or representing the same information. 1 kilometer is 0.6214 miles. We then choose which one of these we want to use for specifically what we have in front of us in order to solve problems. And the basic idea is we then use multiplications and divisions to solve single and multi-step problems. We'll do some examples of this in a different video. But basically, it's where did we start at, our initial units, and then our desired unit. And what we're going to do is we're going to pick the ratio such that the initial units in a numerator and a denominator will cancel. So what the red strike through line means. And then we're going to be left with what we actually want. And in a different video, we'll do some examples of this. We're going to do dimensional analysis problems, but these are going to be in a separate video. We're going to do exactly these 4 problems to illustrate and show you this technique in a different video. So make sure you're watching that video. You may want to print out this specific slide so you can kind of follow along with what we're going to do on the video in the separate video when we're doing these problems. So please make sure you're watching this separate video where we're working through these problems where you can really see that technique in action in order to solve these dimensional analysis problems. We're using these basic unit conversions, miles to inches, kilograms to milligrams, gallons to centiliters. Here's a density, ounces per cup to decilgrams per milliliter, to illustrate the technique. Then, as the semester goes on and on, we'll do even more chemistry-related problems, more chemistry-specific problems using this technique. So a little bit on density. Density is the ratio of a substance mass to its volume. Sometimes it's expressed in kind of formula form. Sometimes you see the D equals M over V. They really kind of want to shorthand that. It's basically expressing something's mass compared to its volume. So we want to compare things that have high density with things that have low density. So an example of something with a high density would be something like a gold ring. If you kind of feel a gold ring in your hand, it has a pretty high, large mass for the little bit of space that it takes up. It's a dense material, a lot of mass for only a little bit of volume. If you contrast that with something that has a very low density, I think the classic example of low density would be something like popcorn. If you look at a bag of popcorn or even a single piece of popcorn, popcorn doesn't have a lot of mass to it, but it takes up a lot of volume. So that is a very, very low density. So temperature scales, I want to talk a little bit about temperature scales. And I kind of put the equations to convert between one and another. To me, though, that's kind of needless math work. Anybody can use the equations, plug and chug. I'm not a big fan of doing math just for the sake of doing math. So instead of just going through calculations with this that anybody could do if you're really interested, I would much rather talk you through the similarities and the differences between these 2 different temperature scales, because that's what really allows you to understand these different temperature scales. This is just kind of math there on the left. On the right, you can really see the relationships that the actual calculations are based off of. So on the left-hand side, we have Fahrenheit, in the middle is Celsius, and on the right-hand side is Kelvin. So the first thing I want to do is, there are other temperature scales we could put up here as well. But regardless of what temperature scale you are on, different physical things will happen. So I'm going to use, for some of these examples, our most common substance. We want to talk about water. And we know some things about water. Water will freeze. We can talk about the freezing point. We know what the freezing point of water is. Fahrenheit, 32. Celsius, 0. Kelvin, turns out to be 273. There's something else we know about water. Water will freeze, water will boil. Whether we put it on a temperature scale, which is a man-made event, or a human invention or not, that doesn't stop water from freezing and boiling. So we also know what water boils at. Water boils at 212 Fahrenheit, 100 Celsius, and 373 Kelvin. So right away, just with this information, we can do a little comparing and contrasting between the temperature scales. The first thing we can say is that Celsius and Kelvin have the same unit size. What do I mean by unit size? That means for water, in Celsius, from freezing to boiling is 100 units, 0 to 100. The difference there is 100. In Kelvin, 273 to 373, that's still 100 units. Celsius and Kelvin will have the exact same Celsius and Kelvin have the exact same unit size. Each unit represents the same amount. Fahrenheit, though, has a different unit size. Look at what happened to water for Fahrenheit, 32 to 212. The difference there is 180 units. So for water going from freezing to boiling in Celsius or Kelvin, it was 100 units. In Fahrenheit, it was 180. So what that means is that Fahrenheit has a different unit size than Celsius and Kelvin does. The unit size on Fahrenheit is smaller. It takes more units to get to the same events. So that's going to be our first kind of difference, comparing and contrasting these different temperature scales. Celsius and Kelvin, same unit size. Fahrenheit, different unit size. The next thing we can kind of look at is there's a theoretical lowest possible temperature. And on Celsius, that's negative 273. Fahrenheit, it's minus 459. And Kelvin is 0. You can't get any colder than that. This kind of shows the next thing that we can kind of compare and contrast between these three different temperature scales. Kelvin is sometimes called the absolute temperature scale. It's called the absolute temperature scale because it can't ever be negative. 0 is as low as it can go. Fahrenheit and Celsius, though, we can definitely have negative numbers there. So that's the similarity between Fahrenheit and Celsius, the ability to have negative numbers. Kelvin would be different in that you can't have negative numbers. And this kind of explains a little bit how these equations actually work. And again, we're not going to just go randomly plug numbers in to convert one temperature to another temperature. That kind of doesn't get us anywhere. But we can see the relationship. When we talk about the relationship between Celsius and Kelvin, well, being they have the same temperature size, same unit size, what we can see is that it's a pretty quick conversion. We just have to bring the points to each other. Celsius and Kelvin are really only different by 273 degrees either way. Kelvin will always be 273 degrees higher than Celsius. That's just the way it always is. When we look at Fahrenheit and Celsius, converting between these two, you see it's a little bit more involved equation because two things have to happen. One, you kind of have to reset the 0 point. That's why you have this plus and minus 32 degrees here. The other thing that you have to do is you have to adjust for the unit size, because Fahrenheit and Celsius have different unit sizes. So that's what the 5/9 and the 9/5 go. You may have seen it as 1.8 multiplied or divide, kind of in a decimal form instead of a fraction. But where did that 9/5 or 5/9 come from? Well, that's the unit size difference. 180 units here for Fahrenheit is only 100 units for Celsius. So 180 over 100, well, that could be reduced to 9/5. That's where you're getting that 9/5. Or 100 over 180 would then also reduce down to 5/9. That's where you're seeing these things coming from. But again, I want you not to necessarily worry about plugging numbers into an equation. We can do that. There are apps for that. That doesn't really show an understanding of the temperature scales. What really shows an understanding of the temperature scales is understanding, hey, Celsius and Kelvin have the same unit size. Fahrenheit has a different unit size than Celsius and Kelvin. It's smaller units for Fahrenheit. Also, recognizing that Celsius and Fahrenheit can go negative. Meanwhile, Kelvin can't be negative. As low as you can go in Kelvin is that 0, that absolute 0 idea.